So, I'm going to introduce you, Emanulele Fabbiani, head of machine learning.
Okay, thank you very much for having me. Tonight we will talk about asyncio. Asyncio, among all the packages of the Python standard library, is one. Oh, what? Oh, sorry. Is one that had a lot of changes in the last few releases. For instance, it was not even there in the earliest version of Python 3.x. And now it is powering frameworks like FastAPI and many SDKs of cloud providers. So it went from being basically just an idea, just a concept, to be one of the backbones of serverless REST APIs and web applications. Asynchronous programming may be intimidating at first, but it's one of the easiest ways to achieve concurrency. In the next 40 minutes, I will try to give you some guidelines and some advice to start using asyncio, to know when to use it and to know how to use it. In order to do so, we need to start somewhere, and of course, what better place to start than a McDonald's? Because if you think about that, when you go to a McDonald's, of course, we're not going to do that afterwards. We're going to a much better place. But anyway, when you go to a McDonald's, what happens is that you go to the waiter, you tell her your order, and then you stand there and wait for something to happen. What is going to happen is that the waiter is going to pass your order to the kitchen, and then it's going to serve other customers. So, in fact, you have one resource, the waiter, that is serving many customers, but this is possible just because there is another actor, the kitchen, which is taking an awful long time to prepare your meal. Of course, you're there, standing, you're hungry, you get angry, and things become worse and worse when you get the meal. But in principle, this is a very interesting idea. You exploit the waiting time to do other stuff, even if you have just one resource doing the job. So again, one waiter who can serve multiple customers just because both of them are waiting for another actor which has cycles way longer than the first one to do his job. Very well, this is a much different situation from the one you live in a post office. In a post office, you have many clerks that are waiting there, doing nothing, absolutely nothing, waiting for you to go, choose one of them, and basically driving crazy. But there are many clerks, you can pick one of them. As soon as one gets free, a customer goes there and the clerk starts serving the customer. As long as the customer is there at the clerk is working. There is nothing else he or she should wait. So getting out of the metaphor, this is real parallelism. Here at the post office, you have multiple resources doing job at the same time. In the McDonald's, this is not parallelism. It gives the idea of parallelism to customers because multiple customers are being served at the same time, but actually the resource is one and one only. There is only one waiter. Very good. It gets more complex than this. In Python, you have 3 ways of achieving concurrency. Concurrency is basically the concept of doing things in parallel, which can be seen as actual parallelism or just giving the impression of doing things in parallel. You have just one way in pure Python code to achieve parallelism, and this is by using multiprocessing.
you have to spawn multiple processes to achieve parallelism in Python because of the global interpreter lock. The GIL is a mechanism designed to prevent concurrency issues at the level of the Python interpreter that is designed to allow just one thread to be executed by the Python interpreter at any given time. So if you want to get parallelism in Python, you have to spawn multiple processes executing different interpreters at the same time. This is, by the way, in pure Python code. I'm not talking about extension written in C or in Rust or in other languages. But apart from that, you have two other ways of achieving concurrency. That is threading and asynchronous programming. This is different. If you use threading, that was the first concurrency method implemented in Python, you delegate the scheduling to the operating system. So you spawn threads that are operating system objects, exactly like processes, and then you give the operating system the task of scheduling threads. So you control the threads, but you do not control when each of them is executing. This is done by the operating system at the lower level. In asyncio, you control when the task stops and when it regains control. It is a much easier method to get concurrency, but of course it has its rules, and we're going to see them very quickly in a few seconds. Why should we care about concurrency? Can't we just run normal synchronous code? We could, and in many cases it's the right way to do it. But in many circumstances, in fact, in every web application, we are wasting most of the CPU time just staying there and waiting. Think about an API that has to call the database to provide some data to the caller. The API gets the request, then executes some code, and then calls the database to fetch the data it needs. When you call the database, basically you're giving away the control to some lower level driver, and then you're standing there and waiting for the data to be fetched from the database. This is, of course, a much longer time than the one it is required to execute the code in your API, and the CPU is basically standing there waiting, doing nothing. Wouldn't it be more sensible if you can just give away the control of the CPU and let it execute other Python code? Asyncio is what allows you to do that. Just to give you an idea of the timescales in play, let's assume that an access to the L1 cache, the fuzz of memory outside the registry built in the CPU itself, takes 3 seconds. Actually, it's 3 CPU cycles, which is some nanosecond. But to get to the human scale, let's go to 3 seconds. Then, if this is true, taking the proportion, the time you need to access the disk is 1.3 years. We're going from seconds to years. And the time you need to perform an HTTP request and to get a response is about 7.6 years, of course, if you have a fast network, that is. So we're going to set from seconds to years, and if you don't use concurrency, your CPU is standing idle and waiting literally for years. Now, the best way to understand how to use asyncio is, of course, using it. And so let's go live coding. And that's a great iguana. I hope that everything works now. Okay.
Lo streaming non funziona così bene. Guarda, sei ancora di nuovo.
Okay. Disable video. Screen share.
persuaded. Grazie.
Great. Very good. So this is a very simple hello world using asyncio. Following Guido's advice, when you read concurrent code written in asyncio, just pretend that async and await are not there and read the code as if it was synchronous, because that's basically what's happening under the hood. So you have a main function which prints something, then we sleep for 1 second, and then we print something else. Okay, the only strange things here are these await, async keywords, and the fact that we are not using time.sleep, but we're using asyncio.sleep. But here is something even better. We're not calling the main function, and actually it's not a function, but we're not calling the main function, we're using asyncio.run. This is available from Python 3.7, by the way. In earlier version, you had to do something more tricky to do the same thing. Okay, why on earth are we using asyncio.run? Why can't we just call main as if it was a normal function? Well, because when you run asyncio.run, what happens is actually this. I've oversimplified here. There are many other things that are happening under the hood, but this is basically the idea. So what asyncio is doing is creating an event loop, then is trying to have the event loop execute the main, and then either it gets an exception or the main terminates, and you have the finally that closes the event loop. Good. What on earth is an event loop then? An event loop is something which was made famous by Node, and then Python implemented itself, and it's something like this. So an event loop is built inside asyncio. It's a module that gets a task queue. When you do asyncio.run and you pass the main to the asyncio.run, what happens is that main goes into a task queue. It gets wrapped into a task and goes into a task queue. Then the event loop starts what is actually an infinite cycle, an infinite loop. At each iteration of the loop, it monitors if there are some tasks that can be run. In this case, main is not waiting for anything, so it gets run immediately. It runs this task until it gets to the first await keyword. In the first await keyword, you are telling Python, look, now I'm calling an awaitable, which is either a task or a coroutine. We will see it later. But here I am going to wait for something else to happen outside of my code. What am I waiting for? Well, in the case of asyncio.time.sleep, I'm just waiting for 1 second to pass. But in that second, I do not want to block the CPU. So I'm handing over the control to you, Python, do whatever you want, and then wake me up when September ends. Wake me up when the second has passed. Very good, but who wakes up the task, which is sleeping? Of course, it must be someone else. It's the operating system. So both Linux, macOS, and Windows have primitives to handle events. So when you await something, you're basically transferring the control of that something to the operating system, which takes over and sends an event when the task is completed. The events get sent to the task, and the task basically raises a flag saying, look, event loop, next time you come to me, you can execute me again. So what happens is, asyncio.run main the task queue. Is main ready to be executed? Yes, go, execute it. Await, asyncio.sleep. Okay, there is an await. Stop here, hand over the control. CPU is, not CPU actually, but the core when the Python main thread is running is free here. Other tasks can run if there are other tasks, that is. Operating system, please wake up the main function when asyncio.sleep is completed. Asyncio.sleep gets completed after 1 second. It raises a flag. The event loop knows that it can start the execution again from that exact point, and the execution is then completed. That's the only awaitable in the event loop. The event loop gets closed. This is it. Easy, right? Let's see what we can break, because that's what we like to do. Let's go into the easier version, and let's see what happens if we don't do asyncio.run, for example. We just call the function main. And here we go. Very good. Runtime warning. Nothing gets printed. So we don't see hello, we don't see word. We just see this very awful runtime warning saying coroutine main was never awaited. Very good. So I have defined a coroutine using async, and I'm not awaiting it. That means that I'm doing nothing. Python is warning me that I'm not using a coroutine in the way that it's meant to be used. And then, of course, this other runtime warning that says that I'm allocating memory and then I'm doing something strange with it. So why a coroutine, and what's a coroutine then? Let's print what main is. And on it. Main is not a function, it's a coroutine object. You probably have seen these kind of printouts before. It's the exact same time, it's the exact same thing that happens with generators. This is not by chance. Async.io is entirely based on generators, but this is a topic for later. But main is not a function, it's a coroutine object, so you cannot just call it with the bracket operator, right? Very good. Coroutines can get executed just inside the event loop, because the event loop is the only object in Python that has the ability to understand what await means. So basically, if you run a coroutine inside the event loop, the coroutine can stop and then start executing again. If you try to call a coroutine outside an event loop, it does absolutely nothing. It does not get scheduled. It does not get executed. It does nothing. So let's go back to normality. There we go. Okay, that's great. How can we use these new ideas to achieve something useful? So let's consider this example then. Here we are basically timing what happens between line 11 and line 14. And what happened is we are calling 3 times the function sendCrow. SendCrow is because I'm a fan of Game of Thrones, of course, and I'm sending out 3 crows to deliver messages to someone. In this function, I'm actually doing nothing, just sleeping for 1 second and printing out when the function starts and when the function ends. If we run this function, there is no async.io here, there is no async, there's no await, so this is completely synchronous code. It gets executed one line after the other. What we expect to happen is that the first call to the function begins, then it ends, the second begins, then it ends, and so on, and it takes exactly 3 seconds to execute the entire program. Of course, we can do better, because for exactly 3 seconds out of 3.016, we're waiting. We're doing nothing. We're just executing time.sleep that has the thread idle. So we can rewrite this exact example in asynchronous code. Let's split the screen and see the differences. So here, sendCrow is no longer a function, it's a coroutine. It's defined with the async keyword. So now I can no longer execute it, I have to await it. It's a coroutine because inside we want to use await to hand over the control to other Python coroutines, to the main event loop, when we sleep. So during this second, other tasks can be executed. And here we do exactly the same thing, apart from the fact that we await the coroutine, we do not just call it. Of course, we have to run asyncio.run. We cannot just call main because even main is a coroutine. So here you see one of the, maybe the basic rule of asyncio. You can await just inside a coroutine. Again, because being a coroutine, it has the certainty of being executed inside the event loop, and the event loop is the only object which understands what await means. Good. What happens here? We run, and we get exactly the same thing. So it's taking exactly 3 seconds to execute. Why? Because these 3 calls to the sendCrow coroutine get executed sequentially because they are in a for loop. So there is no real concurrency here. I'm freeing up the CPU for some other code to execute, but I have no other code to execute. So I'm doing nothing useful. I'm just messing up with the code. Good. How do we do that then? We use a primitive in asyncio that is asyncio.gather. Asyncio.gather accepts an iterable, a list, for example, or just a number of awaitables. Awaitables can be coroutines, like functions defined with async def, or tasks. We're going to see tasks later, and execute everything concurrently. So what happens here is when we await asyncio.gather, the first sendCrow get executed. Remember, we have just one core, one thread, so there is no real parallelism. Line 6 get executed. We go to line 7, await inside an event loop. That's legitimate. Here we hand over the control to the operating system. Please wake us up when 1 second has passed. But there is the second sendCrow. So we can execute the second sendCrow, line 6, line 7. We are awaiting, handing over the control. Third sendCrow, line 6, line 7, await, hand over the control. At a certain point, exactly 1 second after all of this mess has begun, the operating system will send 3 signals to the 3 coroutines saying, okay, 1 second has passed, please wake up. 1, 2, 3, and they will execute line 8, line 9, and when the last sendCrow has completed, then this asyncio.gather will be waked up as well. And it can proceed to line 15, 16, 17. Right? Let's execute it then. And we see the difference. 1, 2, 3, started, completed, exactly 1 second. So if you want to scrape something, that's a great way to do it. Just send all the requests and then wait for them to come, maybe not all of them, but send batches of requests and then wait for them to come back. Do not wait each and every request sequentially because you're wasting a lot of time keeping the CPU idle. And you can see here, there is no reason to use real parallelism because if you parallelize these tasks over multiple cores, what you're doing is just having 3 cores idle for 1 second. And why? Why should you do that? I mean, you're not training a neural network, you're not exploiting the computational power of the processor, you're just making it wait. Very good. So asyncio.gather takes a set of awaitable and then returns when all the awaitables have completed. What if I want to go past line 14 when the first awaitable has completed? I don't care about the other. I use another primitive of asyncio that is wait. Asyncio.wait has a very similar syntax. It does not take star arg here, so it does not take multiple arguments. It takes a list of awaitable. They must be tasks actually, so we need to call asyncio.createTask here, and then we can pass other arguments like the timeout and return when. Return when it means, okay, when should I consider these coroutine completed? I want to consider it completed when the first of these 3 coroutines has completed. I don't care about the others. Just let them be pending. Of course, this does not mean that they get cancelled. So when you run asyncio.wait with this parameter, it means that done will have one element, maybe more if some of them fail, but in case everything is good, it has just one element. Pending has multiple elements, and the event loop will continue on executing the pending coroutines until they're completed. And you have references to them because you have the pending list with the coroutines that are still running in there. Very good. Here there is a timeout. This is kind of tricky because the timeout means, okay, if you run for 10 seconds and nothing is done yet, then give me an empty list here, put everything here, and go past. It does not mean please cancel everything. So you have still coroutines running if you get to the timeout. That's kind of strange, but the documentation of asyncio explains everything. So we can run this example as well. And we can see that only cloud1 return gets printed because after the first coroutine completes, then the event loop knows that asyncio.wait has completed, so it can resume the execution of main. Main completes. This is an asyncio.run, so it means please close the event loop after the coroutine I pass you has completed. So main has completed. There are other 2 coroutines pending. Who cares? The program is over. So you're losing 2 coroutines. It may be okay for you. It may be not. If it is not, just use gather. Okay. I keep saying coroutines. These are tasks actually. A task is a wrapper object which takes a coroutine and provides some more metadata about that. For example, it can tell you if the coroutine is running, if the coroutine has completed, if it has got an exception, and so on. Very good. Talking about tasks, I've said at the beginning that asyncio is one of the packages in the standard library that has seen the most evolutions in the latest years. There is a new syntax to achieve the same thing that I have shown with asyncio.gather, and it's the syntax of task groups. This is brand new, Python 3.11, so you cannot use it if you're not running Python 3.11 or more. This is something strange because you see here that you're doing an async with, so you're using async with the context manager, and then you're breaking the basic rule of asynchronous programming. So you're doing an async which has inside some coroutines, without doing an await. There is no await here. This is not good. This shouldn't work. But if we run it, it does work. What's happening here? So what's happening is that people from Python got really annoyed of getting this runtime warning, you're not awaiting a coroutine over and over and over again. So they said, okay, I will make you a deal. I will give you a context manager, which can be used to schedule in the event loop multiple tasks. And then in the exit of the context manager, I'm awaiting all of them. So that if you forget, I don't. And we can see that. What if we go to the task group and we go to this asynchronous exit? This is the destructor of the context manager. So it's like exit with the A for asynchronous. That's asynchronous exit. And somewhere here, there we go. It just awaits the task for you. So once you get to line 17, when the execution goes past line 17, so you're closing the context manager, every task that got created with task group.createTask gets awaited right there. So it's like using other, but without the risk of not awaiting it. Right? This is going to be the preferred syntax for the next releases of Python. I think that there is still something missing here. So for example, there is no way to do what we did with asyncio.wait. So this async with just awaits everything that gets created. There is no way of saying, look, after the first one, I'm done. But it's going to be improved over the next releases of Python. At least that's what the documentation says. We can also visualize here what are the results. A task is an object. It has methods and attributes. So we can call the result method to get the return value of the coroutine. So coroutines are the basic awaitables. They are defined with async def. Tasks are wrappers of coroutines. Tasks allow you to access the return value of the coroutine with other metadata. Very good. So I'm going along here. So I'm going to show you how to use this stuff in practice, and I'm skipping the error management. Assume that we want to get some data from APIs, right? Assume that we need to call the same API over and over again, maybe with different parameters, to get all our answers. So here what we are doing is actually firing a lot of gets to httpbin.org, not a lot because we don't want to be evil, but we're just sending these requests in batch. Maybe we want to perform some throttling, so we don't want to send 1,000 of requests all in the same batch. We want to send 3 requests at any time. So we use a semaphore. A semaphore is another asyncio primitives that limits concurrency. So it's like saying, okay, asyncio, I want that at maximum 3 coroutines can acquire the semaphore at any given time. Please, asyncio, do that for me. Just let the event loop know and block the execution if a 4th coroutine wants to get executed while 3 are still running. Semaphore supports the context manager, the async context manager, so we can use it with async with. So here in the async with, there may be at most 3 running coroutines in this section right here, lines 12 and 13. So at most 3 requests on the network at any given time. Here we use the task group syntax. Of course, we need to use an asynchronous HTTP library. We cannot use requests. Requests does not support asynchronous calls, and it will not in the future, according to its documentation. So we use HTTPX, which has this async client, very, very handy, and also the async client is an asynchronous context manager. We create 20 tasks, so there are 20 requests that we're going to send, but we want to send them in batches of 3. Then we are going to check how many exceptions we got, how many canceled tasks we got, and print out the results. And then we're going to sum the results, just print out something nice at the end of the script. So basically, this is a very, very complex way to compute the sum of the first 20 natural numbers. And let's go. So here you can see that the printout got in the terminal in batches. So this first, and then at any time that one request was completed, then another one could enter the lines marked with the semaphore, right? And then we got our answer there. Very good. So I have just 20, 50 more slides, but I think my time is over. So it may be for another time when I talk about how asyncio is built on top of generators, because that's a very nice idea to grasp. In Python, asyncio is basically a very ingenious way of using generators. So there you have it. That's a primer of asyncio.
Okay, thank you, Emanuele. Any questions for Emanuele? Okay.
Okay, hi. I'm not sure I completely grasped the main difference between using threads and asyncio. I mean, old school threads with semaphores and mutex. And actually, I have a second question, but after.
Okay, so you can use threads. Threads are much more difficult to use because you have shared memory. You have to be very careful about critical sections in your code. Asyncio is much easier. So basically, the very way in which the idea is built ensures you that there are no critical sections because there is just one thread. So there is no multi-threading there. Moreover, with asyncio, you can explicitly say await. So please stop here, hand over the control, and then wait for some event to happen. With threading, you have either to control explicitly this behavior with variables or other primitives, or just have the operating system schedule the thread for you. And you have no control over which thread is running at any given time. So that's the main difference.
Follow-up question. And what about putting breakpoints for debugging when you're using asyncio? Because if you have other threads running in parallel.
So basically, there is no difference with synchronous code because, of course, there is only one thread. So as soon as the point is reached in the normal execution of the code, the breakpoint is triggered and the execution stops. So you have no situation where the same lines of code is executing in two different threads because there is just the main thread executing the event loop.
Okay. No more questions? Yep.
Hi. So suppose I have, I don't know, the backend that has to execute an option, an action at the end, like a user or fills in a form, and then every field in the form, maybe it's like 50 lines long of a form, it needs to be added to a database behind the backend. I can use asyncio, and every object will be added synchronously, but at the end of the day, I still need for this awaitable to finish before the code gets on and displays, I don't know, the information is sent and you can move on to the next operation? Or can I still leave it hanging, and in the background, the object will still be added to the database?
You can, for a use case like this, usually there is the framework, the web framework like Fast API around your code that is managing, that is doing basically the asyncio.run under the hood. So as long as the asyncio.run, as long as the event loop is running, you can just await that specific action to happen and then leave your front end alone. The response will eventually come.
Okay.
And by the way, if you're using asyncio in this way, when you're waiting for the database query to execute, the thread is free to respond to other requests. So if another user performs some other action, then the CPU is available to execute the actions required by that user. So it's much more convenient for web applications. And that's why Fast API uses asyncio everywhere, basically.
Okay. Any
Will you share the slides that you did not present?
Yes, of course. It's a Google Slide document, so we can put the link in the in the video description and also in the website of Python Milano.
Anyway, you can go to PyCon Italia, and Emanuele will do the same. So it's not a problem having the slides. Any other questions for Emanuele?
Did you have experience with testing with asyncio frameworks to use to unit test? Asyncio?
So the question was, how about testing with asyncio? Okay, PyTest has a great support for asynchronous testing. You can async a test, but then you have to tweak a little bit the execution of the PyTest framework to take it into account. So you can use PyTest in the exact same way that you're using it for everything else by async defining the test.
Okay, I think we reached the 40 minutes. I don't know if there is a very last question or we can say thank you to Emanuele. Okay, next up is Luca. I think we